Questions about anything from before? Or anything? Well, getting near the end of the course. Oh, by the way, I sent an email that I'm extending the due date for the last homework to Friday. That's the last homework 9. So you got some extra time to think about that. I wanted to say a few words about generalized Fourier series, which basically is you do the routine of solving a famous problem, usually by separation of variables, and you might get non-standard functions, which turn out to be orthogonal, and it happens again and again. And these problems lead to a new kind of Fourier series, where it's not quite Fourier series, but it sure feels like Fourier series. And so it's a common experience to run into these things. And I wanted you to see some of the famous ones that come up in practice. I've already mentioned this one. I kind of gave you homework problems related to this, of the hot wire problem with one insulated end. And we've been doing separation of variables. What's happening here? And that's what we're going to do here. But I'm going to show you that when you do separation of variables and play the usual routine, you end up with a new kind of Fourier series that we haven't seen before. Okay, so we're going to do the usual thing. I'm going to take c equal 1 just to make my writing easier. And so we do the usual routine and take a solution here. X of x, u of xt is x of x times t of t. And when you plug that into the differential equation, the PDE, that would be du dt equals, I'm taking c to be 1, so it would be d2u dx squared. And when you put the derivatives on the d by dt, that would hit the t function. So it would be x of x times t prime. And on the u, when you put d2u dx squared, those derivatives would hit the x function. And the t function would act like a constant. And then you can separate. Let's see, I look at that and realize I can pull all the t's to one side and all the x's to the other side. So I get t prime over t equals x double prime over x. And the only way that can be the only way a function of t can be equal to a function of x, as you let the variables range, is if they're both equal to a constant lambda. And let's see, what we have those let's see, I wanted to talk about the boundary condition for a second here. The zero end is going to be an insulated end for this hot wire, and the pi end is going to be held at 0 degrees. Insulated means there's no heat flow. So x equals 0 is the insulated end. That means no heat flow across that spot. And remember, Kelvin's law said that heat flow is proportional to the temperature gradient. And there's a negative constant involved. So Kelvin's law, rate of heat flow in calories per second or minute is equal to minus a constant times the temperature gradient. And the temperature gradient is the derivative of the temperature in the space variable. And so there we go. Sorry, this thing wasn't working. And the temperature gradient at time t would be a derivative in the space variable. That would be a du dx. And so if there is no heat flow, that would have to be 0. And that's why that boundary condition is the insulated one. Insulated boundary condition. And this one's called a homogeneous boundary condition because it's 0. And homogeneous are the best kind, because when you add two things together that satisfy that condition, of course, their sum also satisfies. So this is called a homogeneous boundary condition. Okay, so we've done this routine before. Let's see if we want to translate the boundary conditions into our we have u of x I'm sorry. We have du dx at x equals 0 for all time. Differentiating with respect to x would give me x prime of x, x prime of 0 times t of t. We need that to be equal to 0 for all time. Well, we don't want t of t to be 0, because that would mean the solution is 0. So we don't want t of t to be identically 0, because that would just give us the 0 solution. We only get the 0 solution. So we need the other thing to be 0. We need x prime at 0 to be 0. And the other one is u of pi t. That would be x of pi times t of t. We want that to be identically 0 for all t. So that one, let's see, this one we need x prime of 0 equals 0. This one we need x of pi to be 0. So those are the boundary conditions, and the x, they influence the x function only. Okay, the t problem is easy. Nothing to think about there. The t problem is t prime minus lambda t equals 0 That's easy. That's just exponential decay or growth. That would be T of t equals a constant times e to the, let's see, that's t prime equals lambda t. That would, so the solution would be e to the lambda t. And we can take the c there to be 1. Because we're going to take linear combinations of things when we do that. But the x problem is a more interesting thing. It's called the Sturm-Liouville problem. It's x double prime minus lambda x equals 0. Same old problem, ODE-wise. But new kinds of boundary conditions. X prime of 0. I guess I'll stop making fancy x's. X prime of 0 is 0, and x of pi is 0. So we've got to do cases. Let's see, let's do the case lambda positive. If lambda is positive, we can write, I'm going to have to take the square root of lambda when I solve the ODE. And I don't want to write square root over and over again. So I'm going to take lambda equal k squared, where k is some positive square root. Then the ODE is, the characteristic polynomial for the ODE is r squared minus k squared equals 0, and we get r equals plus or minus k. And we know the solution to that ODE is x of x equals c1 e to the kx plus c2 e to the minus kx. And it turns out that the only way you can make those conditions hold is to take both c's to be 0. So let's see, why is that true? First I better calculate x prime of x. That would be c1k e to the kx minus c2k e to the minus kx. And so when I stick in 0, I get c1k minus c2k equals 0. That's what I want. And so I see that k is not equal to 0, so that tells me that c2 equals c1. Okay, so my x of x is c1 times e to the kx plus e to the minus kx. That's like the hyperbolic cosine. It's 2 times the hyperbolic cosine in the parentheses there. What the heck's going on with this thing? There we go. Okay, so now we can worry about the other endpoint. X at pi would be c1 e to the k pi plus e to the minus k pi. And that's not 0. Well, I want it to be equal to 0. This thing is definitely not 0 because those are 2 strictly positive things. They're both bigger than 1. So we conclude that, ouch, I only get c1 equals 0. I get c1 equals 0, and therefore the solution is the 0 solution. The 0 solution again. And so that's not giving us anything. Then let's see, the lambda equals 0 case. Then the equation would be x double prime equals 0. That's an easy one. And you just integrate it twice and get x of x is ax plus b. Well, x prime of 0 would be a. And I want that to equal to 0. So a is 0. And that means that x of x is just b. And I want x of pi to be equal to 0. So b has to be 0. And I want that to equal to 0, so I get the 0 solution again. So we struck out in this case also. Get the 0 solution again. So hopefully something more interesting is going to happen in this last case of lambda negative. Then we write lambda equal minus k squared, or k is a positive thing. And we get the characteristic polynomial r squared plus k squared equals 0, and we know that's the case where you get trigonometric functions. And let's see, so we get c1 cosine kx plus c2 sine kx. And let's think, I better calculate the derivative before I go anywhere next. So x prime of x would be minus c1k sine kx plus c2k cosine kx. And so when I stick in 0, I get x prime of 0 is, sine of 0 is 0, so it's just c2k. And I want that to be 0. So things are looking bad again. I get that C2 is 0. And so my function is just going to be C1 cosine kx. And so now the last thing I need is the other end to be 0. So x at pi is going to be c1 cosine k pi. And we want that to equal 0. And we don't want c1 to be 0, because then we'd get the 0 solution again. And we'd strike out and get nothing. We don't want c1 equals 0 too, because we would only get the 0 solution. Well, thankfully, cosine wiggles. And it's going to be possible to make cosine wiggle just right so that cosine k pi is 0. So that's the key. So this is going to be a little different than other times we've done this. We need cosine k pi equals 0. And the graph of cosine, everybody knows well. Let's see, we only care about positive x. Cosine of 0 is 1, and then it has a whole bunch of zeros. Let's think about where those zeros are. This is pi over 2, This is pi later. This would be 3 pi over 2. This next one would be 5 pi over 2. And 7 pi over 2, etc. Or you could think of that as, let's write, we need, so this is a graph of cosine x. Or maybe I'll say, yeah, cosine theta. If that's going to be 0, we need k pi to be equal to, let's see, these things are pi over 2 plus a multiple of pi. And let's see, the n there, the first one is n equals 0. So it would be n equals 0, 1, 2, etc. And so let's see, that means my k, when I cancel out the pi, is going to be n plus a half, as n goes from 0, 1, 2, 3, etc. And my lambda now was minus k squared. And that's minus n plus a half squared. So remember what my x function was. My x function was, it's going to depend on x. xn of x is a constant. I called it c1. I'll take that c1 to be 1 in a second. And it was cosine kx. And my k's here are n plus a half. X. And let's see, my t, now I can think about my t problem. My Tn of t was c1, what was it? It was e to the lambda t. And that lambda is minus k squared, so it's going to be e to the minus n plus a half squared t. Those die away really fast. That's kind of interesting. And that's because when you slap a refrigerator on one end of a wire and insulate the left end, it's going to suck all the heat out, and it's going to do it pretty fast. So I'm going to take the C1 to be 1 here. Because later I'm going to take linear combinations of my solutions, my basic solutions, which are now the xn of x times tn of t. That's e to the minus n plus a half squared t cosine n plus a half x. And so, of course, that's not enough to get any old initial condition. I haven't worried about the initial condition yet. So finally, this is kind of a review of things we've experienced before. What's different is we're not going to get Fourier series out of it. We're going to get something kind of new and interesting. Finally, think about the boundary, initial conditions. Well, certainly those don't satisfy, it satisfies a very specific initial condition. If I wanted a generic initial condition, you'd think I might need linear combinations. And of course, finitely many wouldn't be enough. So the big idea is the Fourier series idea. Try u of xt is a linear combination. So it'd be a sum of these things. And let's take coefficients in front. How about a sub n's? minus n plus a half squared t cosine n plus a half t on x, rather. Finitely many wouldn't be enough, and probably we have to take infinitely many. And who knows, maybe that's not enough, because that doesn't look like a full Fourier series. And so the initial condition now is u of x at time 0. Those e to the t's would all be 1. And so that's going to be kind of looking like a Fourier series. This is going to pin down the coefficients. And we want that to be a given function, f of x, an initial temperature. Okay, that's a generalized Fourier series, because it's definitely not what we're used to there. And this happens very often when you have a Sturm-Liouville problem, that you get some kind of generalized Fourier series. In fact, it's a feature of Sturm-Liouville problems that you always get orthogonal functions. And so the big question is, okay, you get these orthogonal functions. The theory would be just the same as Fourier series. And then you ask yourself, are they complete? Do I get a Parsifal's identity? And can I make the whole thing work? And the answer is always yes, it's going to work. So that's where they come from. It means if you understand Fourier series, the classic ones, you understand all these things. And you can make a theory out of them that works. Of course, I'm not going to do that over and over again. If you study this kind of thing more deeply, you would study the general Sturm-Liouville problems and come up with proofs of all the basic facts. But recall, let's see, so that's going to determine, so the good news, the functions you get from a Sturm-Liouville problem of the type we study here are guaranteed to be orthogonal. And so you get a Fourier series idea. And so I can multiply, that determines those coefficients. Let's see, so those cosine functions, even though it doesn't look like I have enough, are orthogonal. And that means if I multiply through by that 1, I would get an times the integral from 0 to pi of cosine squared n plus a half x is equal to the integral dx is equal to the integral from 0 to pi of f of x times cosine n plus a half x dx. And this is an easy thing to calculate, this integral here, because cosine squared, let's see, is 1/2 times 1 plus 2 cosine, what is it? No, what is this thing? Cosine 2 times n plus a half. X. Is that what it is? Pretty sure. Anyway, that's an easy integral from freshman calculus. And that determines the ANs. by this formula. And that's the solution. And you can use Maple and determine that sure enough, it looks like it's working, it converges probably, and you can make graphs and see it all works by this formula. An interesting question is that a complete orthogonal set? So if I take all those functions, cosine n plus a half x, as n goes from 0 to infinity, the word complete means when you have a Parseval's identity, it's an equality. So the Bessel's inequality becomes an equality. A complete orthogonal set. System. And that's the basic question is Bessel's inequality an equality? And when it's an equality, it's called Parseval's identity. That turns out to be equivalent to any concept of completeness. Well, in this particular case, we can do something sneaky. Let's see, we've done the sneaky thing in the past. So sneaky things we've done in the past. For example, we had sine nx n equal 1 to infinity on the interval from 0 to pi. When we looked at that, let's see, what did we do? We had a function f and I extended it to be odd. And then I extended it to be 2 pi periodic. And the full Fourier series for that function had no cosine terms. So then extend to be 2 pi periodic. Let's see, yeah. Extend to be 2 pi periodic. And then the full Fourier series that we studied and understood, the full Fourier series for this odd function has no cosine terms. That was an easy calculation. It means that all we needed was sine on the interval from 0 to pi. So that's how we showed that the sine nx are complete. A complete orthogonal system on 0 pi. Well, it turns out we can do something similar with these cosine terms. Let's see, we also did it for the cosine series. Then we took an even extension. So similarly, by taking an even extension, we also see that the cosine ones are complete. Oops, we also need 1 in this case. 1 comma cosine nth x. It then goes from 1 to infinity, are complete. Need the constant term. Well, what can we do with this cosine n plus halves? Let's think about it. Let me think. Let's see, cosine n plus a half, as n goes from 0 to infinity, is 1/2, 3/2, 5/2, the odd numbers times a half. Let's see here. 1, 3, 5, 7. Uh-oh.
Why does this show that it's complete?
What?
Why does this show that this?
I can make this series converge to any function. I extend it as an even function, and I play these games, and I know that Fourier series converge. So there are enough functions. If I didn't have enough, there would be something I couldn't get. Like if I didn't toss in 1, I'd realize, I don't have enough functions because I can't approximate 1 with those functions. So that's the completeness means I have enough to expand any function in terms of those functions. If I skipped 1, I wouldn't have enough. Just 1. Let's see, 1. Oh, I think I'm going to get confused here. You can get desperate and try various things and think about it. So let's see, what would I do? I've got a function from 0 to pi. Let's see, that 2 in the denominator makes me think of maybe my period isn't the right thing. 1, 3, 5. Oh, blast. I didn't write this down right in my notes. Let's see, if I was going to be desperate, get cosine. Okay, I think I'll save this for next time because I'm going to get desperate. I'm not going to do it today because even though I am desperate, I messed something up in my notes. Get desperate. Try various kinds of extensions of functions to various intervals. So get desperate. Try various types of clever extensions to intervals to make certain terms in the Fourier series cut out. So to intervals to make various terms in the Fourier series cut out. And in this case, it would be all the sine terms and half of the cosine terms. Or I guess I use capital F. Let's see. So what various things you could do. I've got a function from 0 to pi. What does it look like? Maybe it would look like 0 to pi, and it's 0. Yeah, something like that. Well, then I would, step 1 is this is 0 to pi. I can go to 0 to 2 pi. Let's see. I want cosine terms. So I'm going to copy this. I'll make it, copy it. And I'll turn it inside out. Do I need to shrink it a little bit? Looks like it. Kind of like that. So I made it symmetric about pi. Let me make it green. And then I can take the even extension of that. So next, take the even extension. That would be hard for me to do, but I want cosine functions only. Take the even extension. And that would bring me over here to 4 pi, minus 4 pi. No, that's minus 2 pi. So let's see. That would give me something that looks like this. That's supposed to look symmetric. I suppose I can do this, can't I? Sorry. Let's see, so I got to turn that inside out. Hook it up like this. Make it blue. And then finally I need this one. Do I need to turn that in? No, I don't need that one, sorry. I need this one. There. So what I do, I did a symmetric thing from pi to 2 pi, and then I extended it as an even function. So here's minus 2 pi. That sure doesn't look right, but that's what I'm thinking. Pi. So it's symmetric about this way. I've got a function from 0 to pi. I symmetrically make it symmetric about pi. Then I take the even extension, and then I take the 4 pi periodic extension. And then the fact is that Fourier series, the full Fourier series, on the interval from minus 4 pi to 4 pi restricted to 0 pi has a whole bunch of missing has missing things. And it turns out it has just the right missing things. So the full Fourier series on this restricted to 0 pi has just the right missing terms. There's no sine terms, and it's going to cut out every other cosine terms. So it has just the right missing terms to see that we have a complete system. So if you're desperate and you want to prove this without doing anything new, then you can actually do it. To see we have a complete system. Okay, I'm not going to make you do things like this, but it's something that books do rather than start the whole theory from scratch and do general things about Sturm-Liouville problems. They can quite often do something ad hoc. Otherwise, invent the theory of generalized Fourier series. It's kind of a repeat. The whole theory of basic Fourier series in a more general context of Sturm-Liouville problems. Which, if you're going to look at books that do this, especially in engineering, that's what you're going to run into. Okay, we're not going to do that because we're running out of a semester. And that's kind of all I'm going to say about it. But next time I want to do one last famous example to show where Bessel functions come into the whole business. I want to do the vibrating circular drumhead, which is pretty interesting. And we're going to get Bessel functions which are orthogonal. I'm not going to dwell on the technical parts of it. I just want to show you where they come from. So vibrating circular drumhead is considerably different than the square drumhead that I talked about in my video on Friday. Vibrating circular drumhead. And the exciting thing is that that's where the first instance of Bessel functions come up. And they turn out to give us orthogonal functions that we need to solve that problem. Okay, it's kind of a fun thing to see, and it's, I'm not going to dwell on technical things. I just want you to see where they come from. And I think that'll sort of bring us to the end of the subject matter of the course. And then next week I'll review, and I'll be giving you practice problems to do. And think that's the plan. Any last minute questions about anything? Okay.